Somewhere tonight, far beyond the quiet constellations above Earth, a dead star is resisting collapse. A sphere no wider than a city is holding back the weight of an entire sun. Gravity is pulling inward with such violence that space itself bends around the object. And yet, the star remains standing. Not alive in the way ordinary stars are alive. No nuclear fire burns in its heart anymore. No gentle fusion lights its core. By every instinct we have about matter, it should have disappeared long ago into a black hole. But it didn't. And the reason why may be one of the strangest truths in the universe. If you've ever wondered what happens at the absolute edge between matter and collapse, this story connects beautifully with our exploration of black holes that whisper through empty space, where gravity begins to erase the shape of reality itself. Tonight, though, we remain just before that final boundary. Welcome to Velarin's Sleepy Space Mysteries, where tonight we drift slowly into the strange quantum heart of neutron stars, the impossible remnants of gigantic suns that somehow refuse to vanish. Before we continue, take a quiet moment to subscribe, leave a like, turn on notifications, and if you enjoy these long cosmic journeys, you can also join the channel membership to travel even deeper into the universe with future explorations. And as always, let me know gently in the comments, where are you watching from tonight? Perhaps from a quiet city apartment while rain taps softly against the window. Perhaps from a dark countryside beneath real stars. Or perhaps from somewhere far past midnight where the world has already fallen asleep. Now settle in, because tonight we begin with the death of a star so massive, so heavy, that when its core finally collapsed, atoms themselves were crushed out of existence. And yet somehow, the collapse stopped. A neutron star begins its life inside catastrophe. Long before the universe ever creates one of these impossible objects, there is only a massive star living quietly in the darkness, shining with such brightness that entire planetary systems would glow beneath its light like grains of dust beside a furnace. These stars are not calm like our sun. They live fast and violently, burning through their fuel with enormous hunger, pouring unimaginable amounts of energy into surrounding space every second. Deep inside their cores, hydrogen atoms are fused together under crushing heat and pressure, slowly transforming into helium while releasing tremendous energy outward. That outward energy is the only thing preventing the star from collapsing under its own weight. For millions of years, gravity pulls inward while nuclear fire pushes outward, and the balance between those two forces creates the stable glowing star we would see from across the galaxy. But all stars are temporary. Even the largest stars cannot burn forever. Eventually, the hydrogen deep within the core begins to disappear, and when that happens, gravity quietly starts reclaiming control. The star responds the only way it can. The core contracts inward, becoming hotter and denser as gravity squeezes it tighter. That rising heat ignites new fusion reactions. Helium begins transforming into carbon. Later, carbon fuses into oxygen, then neon, then silicon. Each stage burns faster than the one before, A giant star may spend millions of years quietly burning hydrogen. Yet near the end of its life, the final stages happen almost unbelievably quickly. Some fusion phases last only months. Some last mere days. The star enters a desperate race against gravity, trying to create enough outward pressure to survive just a little longer. Inside it, layers form like a cosmic onion. Different elements burn in shells surrounding the core, each one feeding the next layer inward. The entire structure trembles on the edge of collapse, and at the very center something deadly begins to accumulate. Iron. Iron is different from every element before it. Fusion up to iron releases energy, helping the star resist gravity. But iron does not give energy back. Iron is the end of the road. When iron atoms fuse together, the reaction consumes energy instead of releasing it. The star suddenly reaches a wall it cannot climb beyond. And yet the iron core keeps growing larger as surrounding layers continue producing more iron above it. Slowly, silently, the dead weight increases at the center of the star. The temperature rises into billions of degrees. The density becomes almost unimaginable. But no new energy is created. The star has run out of ways to survive. Then comes the moment everything changes. When the core grows too massive, gravity finally overwhelms the pressure supporting it. The collapse begins instantly, not slowly like a building crumbling, not gradually like ice melting. The entire core falls inward at a significant fraction of the speed of light. Matter accelerates downward so violently that atoms cannot survive the compression. Electrons are forced directly into protons, merging together to form neutrons. The familiar structure of ordinary matter disappears completely. Empty space inside atoms vanishes. It is crushed out of existence as the core contracts from something roughly the size of Earth down to something no larger than a city. Imagine the mass of an entire star collapsing into a sphere barely 20 kilometers wide. Gravity becomes so powerful during these final moments that reality itself seems to strain beneath the pressure. And yet something astonishing happens. The collapse suddenly slows, not because gravity weakens. Gravity has never been stronger. The inward force is beyond anything human intuition can truly picture. If gravity alone controlled the universe, the collapsing core would continue shrinking forever until a black hole formed immediately. But deep within the compressed sea of neutrons, another law of nature awakens. A law hidden inside quantum mechanics itself. The neutrons resist being forced together any further. Not through heat, not through chemical strength, not through exploding energy. They resist because the universe fundamentally forbids identical particles called fermions from occupying the same quantum state. The neutrons begin pushing back against gravity through something almost ghost-like in its nature. A pressure born not from fire, but from existence itself. This is the strange miracle hidden inside every neutron star. The object survives because reality contains rules deeper than gravity. Quantum mechanics creates a final wall against collapse. The neutrons cannot all be compressed into the same conditions, so pressure emerges naturally from their resistance. The harder gravity squeezes, the harder the neutrons push back. For a brief eternal balance, the universe pauses between destruction and survival. A neutron star is born there, suspended exactly at the edge between matter and oblivion. And perhaps that is what makes neutron stars feel so haunting. They are not truly alive anymore, but they are not entirely dead either. They are frozen remnants of violence, held together by invisible quantum laws operating beneath ordinary reality. In the darkness of space, these tiny collapsed stars continue spinning silently for millions or even billions of years, carrying within them the memory of one of the most violent deaths the cosmos can produce. And the deeper we travel into their strange interiors, the stranger the universe becomes. Because inside a neutron star, gravity is no longer the only master of reality. Quantum mechanics begins rewriting the rules. What makes neutron stars so unsettling is not only their density, but the fact that the universe should not really allow them to exist for long. Every instinct we develop from ordinary life tells us that if enough weight presses inward, eventually everything must collapse. Mountains crumble beneath gravity. Buildings fail under pressure. Even stars themselves eventually lose their balance and fall inward toward destruction. Gravity always seems patient, relentless, impossible to escape. And inside a neutron star, gravity reaches a level so extreme that the surface curves space-time itself into a deep, invisible well. Light leaving the star loses energy climbing upward. Time flows more slowly near its surface compared to faraway regions of space. The star becomes a place where reality bends under pressure like soft fabric pulled downward by enormous weight. Yet despite all of this, the neutron star remains stable for millions or even billions of years, as though the universe has created a tiny forbidden island where collapse pauses indefinitely. To understand why this happens, we have to leave behind ordinary intuition for a while and drift into the strange world beneath visible reality. The quantum world where particles behave less like tiny solid objects and more like waves of probability spread through space. Down there, matter obeys laws that seem almost dreamlike compared to everyday experience. And one of those laws quietly shapes the structure of everything in existence, from atoms inside your body to the survival of neutron stars themselves. Every particle in the universe belongs to one of two great families. There are bosons, particles that happily gather together and share the same conditions without resistance. And there are fermions, particles that absolutely refuse to become identical to one another. Neutrons belong to this second family. So do electrons and protons. In fact, almost all ordinary matter is built from fermions. The chair beneath you, the air around you, your skin, your heartbeat, even the atoms carrying thoughts through your brain are all constructed from particles that obey this strange quantum rule. Two identical fermions cannot occupy the same quantum state at the same time. It is not a suggestion. It is not a tendency. It is one of the deepest rules woven into reality itself. In ordinary life, we never notice this directly, but it quietly shapes the world around us every second. The reason matter feels solid is ultimately connected to this principle. When your hand touches a table, the atoms inside your skin do not actually crash physically into the atoms inside the wood. Instead, the electrons surrounding those atoms resist being pushed into the same states. Quantum mechanics creates an invisible pressure that prevents matter from passing through itself. The solidity of the world emerges from countless tiny refusals happening inside atoms everywhere around us. Inside a neutron star, that same principle becomes unimaginably powerful. As gravity crushes matter tighter and tighter, the neutrons are forced into smaller regions of space. But the more tightly they are compressed, the fewer available quantum states remain. Eventually, the neutrons begin occupying higher and higher energy conditions simply because no lower states are left. This creates a kind of pressure unlike anything in ordinary physics. It is not generated by heat. It does not come from burning fuel or exploding energy. Even if the neutron star cooled to near absolute zero, the pressure would remain. The neutrons resist compression because the laws of quantum mechanics leave them no other choice. This resistance is called degeneracy pressure, and it is one of the strangest forces in existence because it emerges purely from the identity of particles themselves. The neutrons push back against gravity not through effort, not through combustion, but simply because reality forbids them from collapsing into identical existence. It is almost poetic in a strange cosmic way. The star survives because the universe contains a law against perfect sameness. But degeneracy pressure is only part of the story. Deep inside the neutron star, matter is compressed so tightly that neutrons nearly touch one another directly. At these distances, another force awakens, one even more powerful than electromagnetism. The strong nuclear force, the same force that binds atomic nuclei together, begins resisting further compression as well. At slightly larger distances, the strong force attracts particles together, holding nuclei stable. But at extremely tiny separations, it becomes violently repulsive. It is as though nature itself builds a final invisible wall deep inside matter, preventing particles from occupying the same place completely. Together, neutron degeneracy pressure and the repulsive strong force create the balance that keeps neutron stars alive. Gravity pulls inward with unimaginable violence, while quantum mechanics pushes outward with equal determination. Neither side fully wins. And so the neutron star exists suspended exactly between collapse and resistance, between destruction and structure, like a cosmic monument built from tension itself. And yet, the deeper physicists studied neutron stars, the stranger the mystery became. Because the pressures inside these stars are so extreme that even neutrons may not survive unchanged forever. At the very center, conditions become so intense that matter could transform into forms never naturally seen anywhere else in the universe. The neutrons themselves may begin dissolving into seas of free quarks, the deeper particles hidden inside every proton and neutron. Entire new states of matter may exist there, buried beneath layers of crushing gravity and silent darkness. A neutron star may not truly be a star at all anymore. It may be something closer to the exposed skeleton of physics itself, where the universe reveals laws normally hidden far beneath ordinary reality. And somewhere inside those unimaginable depths, another mystery quietly waits. Because even neutron stars, miraculous as they are, cannot resist gravity forever if enough mass is added. There exists a final limit, a point where quantum mechanics itself begins losing the battle. Beyond that boundary, the universe crosses into something even darker, something from which nothing, not even light, can ever return. The existence of neutron stars reveals something deeply unsettling about the universe. It tells us that reality contains boundaries invisible to human senses, thresholds where familiar matter transforms into something almost unrecognizable. And yet, neutron stars are not the final boundary. They are only the last stable step before gravity crosses into complete domination. Somewhere beyond them lies a limit that even quantum mechanics cannot survive. Physicists call this boundary the Tolman-Oppenheimer-Volkoff limit, usually shortened simply to the TOV limit. It represents the maximum mass a neutron star can possess before the pressure inside it finally fails. The exact number is still uncertain because the inner structure of neutron stars remains mysterious, but most estimates place the limit somewhere around 2 to 3 times the mass of our Sun. That may sound enormous, but on cosmic scales it is surprisingly fragile. Add enough matter to a neutron star, and eventually the inward pull of gravity becomes stronger than all quantum resistance combined. This creates one of the strangest situations in astrophysics because neutron stars can continue gaining mass long after they form. Some exist in binary systems beside ordinary stars. Over millions of years, the neutron star slowly steals gas from its companion. The stolen matter spirals inward into a glowing disk heated to extraordinary temperatures before finally crashing onto the neutron star's surface. Little by little, the dead star grows heavier. Gravity strengthens. The interior compresses further. The balance between collapse and resistance becomes more unstable. And all the while, the neutron star spins faster. As falling matter transfers angular momentum, the neutron star begins rotating with astonishing speed. Some spin hundreds of times every second. Imagine an object heavier than the Sun rotating so quickly that an entire revolution takes less time than a blink. These stars become cosmic lighthouses called pulsars. Beams of radiation sweep outward from their magnetic poles across space. Each time the beam crosses Earth, astronomers detect a pulse. Some pulsars are so precise that they rival atomic clocks in accuracy, maintaining nearly perfect rhythm across millions of years. Deep inside their crushing gravity, nature somehow produces extraordinary order. But beneath that stability, gravity continues waiting patiently. If enough additional matter accumulates, the neutron star approaches the final threshold where no known force can save it. And what happens next is not simply an explosion or collapse in the ordinary sense. It is the destruction of structure itself. The moment the star crosses beyond the TOV limit, gravity overwhelms degeneracy pressure completely. The neutrons can no longer resist compression. The inward collapse resumes catastrophically. The star shrinks smaller and smaller, faster and faster, until eventually something extraordinary happens to space-time itself. An event horizon forms. This is the true birth of a black hole. Not an object sitting inside space like a dark planet, but a region where gravity curves space-time so severely that every possible future path leads inward. Beyond the event horizon, escape ceases to exist even in principle. Light cannot leave. Information cannot return. To outside observers, the collapsing star appears to freeze and fade near the horizon as time itself becomes distorted by gravity. But from the perspective of the falling matter, collapse continues inward relentlessly toward a point where known physics breaks apart completely. And this is what makes neutron stars feel almost tragic in a cosmic sense. They are temporary victories against gravity. Magnificent ones, but temporary nonetheless. Quantum mechanics can resist enormous compression, enough to halt the collapse of an entire stellar core, but even those deep laws of nature possess limits. Add enough mass, and gravity eventually crushes through every defense the universe can build. Yet strangely, neutron stars may also help humanity understand black holes themselves. Because unlike black holes, neutron stars still possess visible structure. They still emit light. They still reveal information about the behavior of matter under extreme conditions. In many ways, they are the last observable stage before reality disappears behind the curtain of an event horizon. By studying neutron stars, astronomers are studying the edge of known physics. And what they continue discovering is increasingly bizarre. Some neutron stars possess magnetic fields so powerful that they distort atoms themselves. These rare objects, called magnetars, contain the strongest magnetic fields known anywhere in the universe. If one passed halfway between Earth and the Moon, its magnetic field could erase information from every computer on Earth instantly. Closer still, the magnetic forces would begin tearing apart molecular structures inside living tissue. Reality near a magnetar becomes almost unrecognizable. Even empty space behaves differently. Light passing through the surrounding vacuum can split and bend as though space itself has become a crystal. Other neutron stars collide with one another in violent mergers that shake space-time across the cosmos. When two neutron stars spiral together and crash, they release enormous bursts of gravitational waves, ripples traveling through space-time itself. In 2017, astronomers detected one of these collisions for the first time. For a brief moment, humanity witnessed the merging of two dead stars over 100 million light-years away. The collision produced gold, platinum, and other heavy elements before collapsing into darkness. In a very real sense, some of the gold on Earth may have been forged during ancient neutron star collisions long before our solar system even existed. So when you hold a piece of gold jewelry in your hand, you may be touching the ashes of dead neutron stars. Matter that once existed inside collapsed stellar remnants under crushing gravity before being scattered across galaxies by cosmic violence. The universe is deeply interconnected in ways almost impossible to feel during ordinary life. The atoms around us carry memories of ancient stars, ancient explosions, ancient collapses. And perhaps that is why neutron stars feel so hauntingly beautiful. They are not merely astronomical objects. They are reminders that the universe is built from tension between opposing truths: gravity and quantum mechanics, collapse and resistance, destruction and structure. Even existence itself may emerge from those invisible balances hidden deep beneath reality. Somewhere tonight, beyond the quiet stars above Earth, a neutron star is still spinning in darkness. Tiny compared to ordinary stars, almost invisible across cosmic distances. Yet inside that silent object, the strongest known force in nature continues battling gravity every second, holding back total collapse by the narrowest possible margin. A dead star refusing to disappear, a final island of matter standing at the edge of the abyss. For most of human history, neutron stars existed only as impossible ideas hidden inside mathematics. No one had ever seen one directly. No telescope in the ancient world could have revealed them. They are far too small, too dark, too distant. And yet somehow, long before humanity fully understood atoms, long before quantum mechanics emerged, the universe had already filled the galaxies with these collapsed remnants quietly spinning through darkness like invisible ruins left behind by dead suns. It was only during the 20th century, after physicists began uncovering the strange laws governing subatomic particles, that the possibility of neutron stars slowly entered scientific thought. Even then, the idea sounded absurd. A star heavier than the sun compressed into a sphere smaller than a city seemed almost beyond belief. The densities involved were so extreme that ordinary language struggled to describe them. How could matter survive such crushing gravity without vanishing entirely into a black hole? Many physicists initially doubted such objects could really exist in nature. The mathematics pointed toward them, but reality often feels less strange than theory. Or at least humans once hoped it did. Then the universe answered in its own quiet way. In 1967, a young graduate student named Jocelyn Bell Burnell was studying radio signals from the sky when she noticed something peculiar hidden inside the data. A tiny repeating pulse, perfectly regular, precise beyond anything naturally known at the time. The signal flashed again and again with exact timing, almost like an artificial beacon broadcasting across space. For a brief moment, some researchers half-jokingly wondered whether the pulses could come from extraterrestrial intelligence. The signal was nicknamed Little Green Men 1, but soon more repeating signals appeared in different regions of the sky, and the mystery deepened. Whatever these objects were, the universe contained many of them, The explanation eventually emerged through theoretical work already waiting quietly in astrophysics. These rhythmic pulses came from rapidly spinning neutron stars. Pulsars. The discovery transformed neutron stars from speculative mathematics into observable reality almost overnight. Imagine standing beside one of these stars, if standing there were somehow possible. A sphere perhaps 20 kilometers across spins dozens or hundreds of times every second while beams of radiation sweep outward from its magnetic poles like enormous cosmic lighthouses. Each rotation sends another pulse across the galaxy. Some pulsars are so stable that their timing rivals the best clocks humanity has ever constructed. Even after millions of years, their rhythm barely changes. Deep within collapsed stellar remnants, nature creates order of astonishing precision. And yet these stars were born from violence beyond ordinary imagination. The supernova explosions that create neutron stars briefly outshine entire galaxies. During those moments, the dying star releases more energy than our sun will emit across its entire lifetime. Shockwaves race outward through space, carrying newly forged heavy elements into surrounding interstellar clouds. Future stars and planets form from that enriched material. Future oceans, future mountains, future living creatures. The calcium in your bones, the iron flowing through your blood, even some of the oxygen you breathe were likely forged long ago inside exploding stars that left neutron stars behind. In this sense, neutron stars are not distant from us at all. They are connected intimately to our own existence. The atoms composing human life passed through ancient stellar furnaces before Earth even formed. Every living thing carries the memory of dead stars hidden inside its chemistry. And perhaps nowhere is that connection more haunting than in the collisions between neutron stars themselves. For billions of years, some neutron stars orbit one another in slow spirals driven by gravity. Each orbit releases tiny amounts of energy through gravitational waves, causing the stars to drift gradually closer together. The process takes unimaginable stretches of time, millions of years, sometimes billions. Two collapsed stars dance endlessly in darkness while space itself slowly steals their orbital energy. Then finally, near the end, everything accelerates. The stars circle faster and faster until eventually they collide in a burst of violence so immense that space-time trembles outward across the cosmos. When astronomers detected such a collision in 2017, it became one of the most extraordinary scientific moments in human history. Humanity observed gravitational waves and light from the same event simultaneously for the first time. The collision occurred over 100 million light-years away, yet instruments on Earth still detected ripples moving through space-time itself. Tiny distortions smaller than atomic nuclei passed through our planet, carrying information from two neutron stars merging in deep cosmic darkness. The collision also answered another ancient mystery. Where do many heavy elements come from? Gold, platinum, uranium, elements too massive to form easily inside ordinary stars. The answer appeared hidden inside neutron star mergers. During those catastrophic collisions, enormous quantities of neutron-rich matter are thrown into space where rapid nuclear reactions create some of the heaviest elements in existence. Entire worlds may ultimately form from the debris of ancient neutron star collisions. There is something strangely beautiful about that idea. Somewhere long before Earth existed, two dead stars spiraled together through darkness and collided. Their shattered matter drifted across interstellar space for millions of years before becoming part of a young solar system. Eventually, some of those atoms became oceans, mountains, living cells, human hands. The universe is not made from isolated events. Everything is connected through ancient cycles of collapse and rebirth stretching across unimaginable time. And still neutron stars continue spinning out there tonight. Some are isolated and quiet now, cooling slowly over billions of years. Others remain active pulsars sweeping invisible beams across the galaxy. Some hide inside binary systems waiting for future collisions. Some may already sit dangerously close to the threshold where gravity will finally overwhelm quantum resistance forever. Because the strange balance inside neutron stars cannot last indefinitely under all conditions. There remains a deeper mystery hidden beneath their surfaces, one physicists still do not fully understand. At the crushing densities inside their cores, matter may transform into forms never before seen. Neutrons themselves may dissolve. Quantum fields may rearrange. Entirely new states of existence may emerge under the pressure. And somewhere beyond those unknown interiors waits the final boundary where even neutron stars disappear completely, collapsing into objects so dark that space-time seals shut around them forever. Inside a neutron star, the universe approaches one of its most mysterious frontiers. Physicists can describe many aspects of these objects with remarkable precision. We understand how massive stars collapse. We understand the role of quantum mechanics in resisting gravity. We understand how pulsars spin and how magnetars unleash colossal bursts of energy. But deep within the very center of a neutron star, there is a region where modern science begins fading into uncertainty. The densities become so extreme that no laboratory on Earth can reproduce them fully. Even our most advanced theories begin struggling there. It is one of the few places in the cosmos where nature may still be hiding entirely unknown forms of matter. To appreciate how strange this is, imagine descending slowly toward the center of a neutron star. The outer crust would already feel utterly alien compared to anything on Earth. Atomic nuclei are packed together inside an immense crystalline lattice while free electrons move through the structure like an ocean of electricity. Deeper still, gravity squeezes the matter harder and harder until neutrons begin leaking out of nuclei entirely. Eventually, the distinction between separate atoms disappears. Ordinary chemistry vanishes. Matter no longer resembles anything familiar from everyday life. And then comes the core. Here the pressure becomes so overwhelming that even neutrons themselves may no longer remain intact. Remember, neutrons are not fundamental particles. They are built from smaller entities called quarks held together by the strong nuclear force. Under ordinary conditions, quarks remain permanently confined inside particles like protons and neutrons. No isolated quark has ever been observed directly in nature. But inside a neutron star core, gravity may compress matter beyond the point where individual neutrons can survive as separate structures. The boundaries between particles may dissolve. Instead of a sea of neutrons, the center of the star could become a strange fluid made of free quarks moving together in enormous density. Some physicists call this quark matter. Others imagine even stranger possibilities involving exotic particles rarely seen elsewhere in the universe. Entire new phases of matter may exist there, hidden beneath kilometers of crushing stellar material and gravitational pressure beyond human imagination. What makes this mystery so fascinating is that neutron stars may contain conditions older than stars themselves. The early universe, just moments after the Big Bang, was likely filled with similarly extreme matter before cooling allowed ordinary particles to form. In a sense, neutron stars may preserve tiny surviving pockets of primordial physics, places where the universe still resembles its earliest moments. Buried inside these dead stars could be echoes from the birth of reality itself. And yet, despite all this violence and density, neutron stars can remain astonishingly stable. Some continue existing for billions of years. Over time, they slowly cool, radiating away leftover heat from their formation. A young neutron star may possess temperatures reaching hundreds of billions of degrees shortly after birth, hotter than almost anything else in the universe. But gradually the heat escapes through streams of ghost-like particles called neutrinos and later through faint thermal radiation from the surface. Eventually the neutron star grows colder and dimmer, yet the quantum pressure inside remains. The star survives not because it stays hot, but because the laws of physics themselves continue resisting collapse. This creates a strange contrast between appearance and reality. From far away, an old neutron star may seem almost invisible, a dark object drifting silently through interstellar space. Yet hidden inside that tiny sphere remains gravity so intense that space-time bends sharply around it. 1 teaspoon of neutron star material would outweigh mountains. One small fragment would carry more mass than entire human civilizations combined. The star may appear quiet from a distance, but internally it remains one of the most extreme places in existence. Sometimes, however, neutron stars remind the universe they are still dangerous. Their crusts can crack under magnetic stress, producing violent starquakes that release enormous bursts of radiation. Their rotation rates can suddenly shift as superfluid interiors interact with the outer crust. In binary systems, they can siphon matter from companion stars until explosive thermonuclear flashes erupt across their surfaces. Even in apparent death, neutron stars remain restless. And perhaps most haunting of all is the possibility that some neutron stars wandering through the galaxy are ancient beyond comprehension. Long after civilizations vanish, long after planets freeze, long after many stars burn out completely, neutron stars may still endure. Their cooling process is incredibly slow. The universe itself is not yet old enough for the oldest neutron stars to have fully faded into darkness. Some of the neutron stars existing tonight may continue surviving trillions of years into the future, long after the familiar age of stars has ended. Imagine that distant future for a moment. Galaxies dimmer, star formation slowing, the bright cosmic era gradually fading into colder darkness. And still, scattered through silent space, tiny neutron stars continue spinning quietly like embers left behind after the great fires of the universe have burned away. There is something strangely melancholic about them. They are remnants of catastrophe that outlive almost everything else. Monuments built from collapse. Silent witnesses to cosmic time. But neutron stars also reveal something hopeful hidden deep inside physics. Gravity, despite all its power, does not rule reality alone. The universe contains deeper laws capable of resisting even the crushing weight of dead stars. Quantum mechanics creates structure where collapse should dominate. Tiny invisible rules governing particles become strong enough to oppose gravity on a cosmic scale. The same principles shaping atoms inside your body help hold together some of the densest objects in existence. In that sense, neutron stars are reminders that the universe is balanced between enormous opposites, vastness and smallness, gravity and quantum mechanics, destruction and survival. The cosmos builds extraordinary things not through simplicity, but through tension between competing truths. And perhaps that is why neutron stars continue captivating human imagination so deeply. They sit precisely at the border where our understanding begins dissolving into mystery. Beyond them waits the black hole, where space-time itself closes inward and information disappears behind horizons from which nothing returns. But neutron stars remain just before that abyss. They are the final visible resistance against total collapse. The last place where matter still survives as matter. Somewhere tonight, one of them is turning slowly through darkness beneath distant constellations, carrying within its tiny surface the weight of an entire dead sun, held together by laws so strange and beautiful that even now humanity has only begun to understand them. There is a quiet paradox hidden inside neutron stars that makes them unlike almost anything else in the universe. They are born in explosions violent enough to outshine galaxies, forged through collapse so intense that atoms themselves are destroyed, and yet after all that chaos, what remains can become extraordinarily stable. A neutron star may spin silently through darkness for billions of years with incredible precision, almost untouched by the passing ages of the cosmos. It is as though the universe briefly unleashes unimaginable violence only to create something cold, quiet, and enduring afterward. Perhaps that is why neutron stars feel less like ordinary astronomical objects and more like cosmic relics. They resemble the fossilized remains of gigantic stars, compressed into tiny spheres where the laws of nature are stretched to their limits but not yet broken. Black holes lie beyond them like complete surrender to gravity, but neutron stars remain balanced delicately at the threshold, resisting the abyss through the strange stubbornness of quantum mechanics. And yet, even after decades of observation, they continue surprising us. One of the strangest discoveries involves the interiors of neutron stars behaving as superfluids. Under the crushing pressures inside these objects, neutrons can enter a bizarre quantum state where friction nearly disappears completely. In ordinary life, motion slowly loses energy. A spinning wheel eventually stops. Ocean waves fade. Air resistance and friction gradually drain movement away from systems everywhere around us. But inside parts of a neutron star, matter may flow forever without slowing down. The neutrons move collectively in a perfectly coordinated quantum state, almost like a single enormous wave extending through the star's interior. This superfluid behavior helps explain mysterious events called pulsar glitches. Normally, pulsars slow down gradually over time as they lose rotational energy. Their rhythm becomes slightly slower year after year. But sometimes astronomers observe sudden tiny jumps where the neutron star unexpectedly spins faster for a brief period. It is as though the star momentarily jerks itself forward against the smooth slowing expected from physics. The likely explanation comes from the strange superfluid hidden inside. Deep beneath the crust, the superfluid interior may continue rotating faster than the outer layers. Over time, tension builds between them. Then suddenly the superfluid transfers angular momentum outward, causing the crust to spin up abruptly before equilibrium slowly returns. Across vast cosmic distances, astronomers can measure these tiny shifts with astonishing precision. Humanity is effectively detecting the internal motion of superfluid matter inside dead stars thousands of light-years away. And that alone feels almost unbelievable. But neutron stars become stranger still when magnetism enters the picture. Some possess magnetic fields so intense that they fundamentally distort the behavior of matter and even the vacuum of space itself. These objects, magnetars, are among the most extreme creations known anywhere in existence. To understand how powerful these fields are, consider this gently. Earth's magnetic field quietly guides compasses and protects us from charged particles streaming from the sun. It is important for life, but relatively weak on cosmic scales. A refrigerator magnet contains a stronger field locally than the planet beneath our feet. But a magnetar's field is trillions of times stronger than Earth's. Near one of these stars, atoms become stretched into unnatural forms. Electron clouds deform. The ordinary structure of matter begins unraveling under magnetic stress. Even light behaves differently there. Normally we think of empty space as exactly that, empty. But according to quantum physics, the vacuum is never truly empty. Tiny quantum fluctuations constantly appear and vanish within it. Near a magnetar, the magnetic field becomes so intense that it alters the vacuum itself, affecting how light travels through surrounding space. In a sense, the emptiness around the star becomes polarized and distorted. Reality near a magnetar no longer behaves the way human intuition expects reality to behave. And occasionally these stars erupt violently. The crust of a neutron star is immensely strong, likely the strongest solid material in the known universe. Yet, on a magnetar, even that crust can fracture under magnetic stress. When it cracks, enormous bursts of X-rays and gamma rays explode outward across space. Some of these eruptions release more energy in a fraction of a second than the sun emits in hundreds of thousands of years. Even from tens of thousands of light years away, such bursts can affect Earth's atmosphere faintly. Imagine that for a moment. A tiny collapsed star no wider than a city, sitting on the far side of the galaxy, releases enough energy to subtly disturb our planet across unimaginable distance. The universe contains powers so vast that human language barely holds them comfortably. And still neutron stars continue teaching us. Every new observation reveals another piece of the puzzle. By measuring their masses and radii, physicists slowly narrow possibilities for what matter becomes under extreme density. By studying gravitational waves from neutron star mergers, astronomers learn how spacetime behaves during colossal collisions. Collapse becomes renewal. The universe wastes nothing completely. Even catastrophe feeds future generations of stars and worlds. In the aftermath of supernova explosions, enriched clouds drift across galaxies until gravity slowly gathers them again into new systems. Somewhere, perhaps right now, young planets are forming from material once compressed inside ancient neutron stars billions of years ago. The cosmos is continuously recycling itself through cycles too large for ordinary human perception. And neutron stars occupy one of the most dramatic stages within that cycle. They represent matter stripped nearly to its final limits without fully disappearing into black holes. A neutron star is what remains when gravity almost wins. Not entirely, but almost. That word matters. Almost. Because everything about these stars exists near boundaries. Their densities approach the limits of known matter. Their gravity approaches the threshold of black hole formation. Their magnetic fields approach the strongest intensities nature allows. Their rotation speeds approach relativistic extremes. They live permanently beside edges where familiar physics begins transforming into something stranger. This is why physicists remain obsessed with them. Every new neutron star discovered provides another opportunity to test theories under conditions impossible on Earth. When astronomers measure tiny changes in pulsar timing, they are testing gravity itself. When gravitational waves from neutron star mergers pass through detectors, scientists glimpse how spacetime behaves under colossal stress. When X-rays from neutron star surfaces are analyzed, researchers gather clues about the structure of ultradense matter hidden deep inside their cores. And despite all our technological progress, neutron stars still hold secrets beyond current understanding. No one knows exactly what exists at their centers. No one fully understands the equation describing matter at such extreme density. Some theories suggest quark matter. Others predict exotic condensates or entirely unknown states. The universe may be hiding new physics inside these stars quietly beyond the reach of present experiments. There is something humbling about that uncertainty. Human civilization often imagines science as a gradual conquest of mystery, but neutron stars remind us that reality remains vastly larger than our understanding. Even after centuries of astronomy and physics, some of the most fundamental questions about matter itself remain unresolved. What is the final stable form of matter before collapse? Can quarks exist freely inside stellar cores? What truly happens at the boundary between neutron stars and black holes? We do not fully know, and perhaps that uncertainty is beautiful in its own way. The universe still contains places where mystery survives intact. Somewhere tonight, beneath distant constellations, countless neutron stars continue turning through silent darkness. Some pulse steadily like cosmic heartbeats. Some drift invisibly between the stars. Some wait in binary systems for future collisions that will shake spacetime itself. Others sit dangerously close to collapse, carrying within them the possibility of becoming black holes at any moment if enough matter falls inward. But for now they endure. Tiny stars heavier than suns. Dead remnants brighter in mystery than in light. Objects held together not by fire, but by invisible quantum laws written into the foundation of existence itself. And as the universe slowly expands across billions of years, those neutron stars will continue their quiet journey through darkness, carrying inside them one of the deepest truths modern science has ever uncovered. That even at the edge of annihilation, reality still resists complete collapse for as long as it possibly can. There is one final reason neutron stars continue fascinating scientists so deeply, and it reaches beyond astronomy into some of the oldest human questions about reality itself. These stars force us to confront an uncomfortable truth. The universe is not built from solid certainty. Beneath everything familiar lies a hidden world governed by probabilities. Invisible fields, warped spacetime, and quantum rules so strange that even the densest stars in existence depend upon them for survival. For most of human history, the night sky appeared calm and eternal. Stars looked permanent, fixed, ancient lights hanging silently above Earth. But modern physics slowly revealed that stars are temporary structures balanced delicately against gravity. Some wait in binary systems beside companion stars, slowly gathering matter that may one day push them beyond the final limit into black holes. And still they endure for now. Tiny spheres no larger than cities holding more mass than suns. Objects where a teaspoon of matter outweighs mountains. Stars supported not by fire, but by the invisible architecture of quantum mechanics itself. Perhaps somewhere very far in the future, long after humanity is gone, many neutron stars will still remain. Galaxies may grow darker. Star formation may fade. The bright age of stellar light may slowly decline across trillions of years. Yet neutron stars could continue traveling silently through the cold, expanding universe like ancient embers refusing to disappear entirely. There is something deeply peaceful about imagining them that way, not as monsters of destruction, but as quiet survivors of cosmic catastrophe. Small dense remnants carrying within them the memory of exploded suns and the strange invisible laws holding reality together. And perhaps that is the final mystery neutron stars leave us with. The universe is not built only from violence or emptiness. Hidden even within collapse are patterns of resistance, balance, and endurance. Gravity may pull relentlessly inward across the cosmos, but somewhere deep inside matter itself, the universe still whispers no. And perhaps the strangest part of all this is that neutron stars are not rare cosmic accidents hidden only in distant corners of the universe. Astronomers estimate that the Milky Way alone may contain hundreds of millions of them drifting silently between the stars. Most are invisible to us. Their surfaces are tiny compared to ordinary stars, and once they cool, they emit very little light. Entire populations of neutron stars may pass unnoticed through the galaxy like dark wandering relics from ancient stellar deaths. Right now, at this very moment, one could be traveling quietly through interstellar darkness relatively close to our solar system without human eyes ever seeing it directly. That thought changes the night sky slightly once you begin feeling its scale. The universe above us is not merely filled with shining stars. Hidden among those lights are collapsed remnants carrying densities and gravitational forces almost impossible for the human mind to picture. Tiny invisible spheres heavier than suns crossing the galaxy in silence. And despite their terrifying properties, neutron stars also produce some of the most beautiful phenomena in the cosmos. When matter falls toward one from a nearby companion star, it spirals inward into an accretion disk glowing brilliantly with heat and radiation. As gas accelerates around the neutron star, friction and gravity raise temperatures high enough to emit intense X-rays visible across enormous distances. The material circles faster and faster before finally crashing onto the surface in violent flashes. In these systems, neutron stars become some of the brightest X-ray sources in entire galaxies. There is something mesmerizing about imagining that process from a safe distance. A collapsed stellar remnant no wider than a city pulling streams of glowing matter from another star while rotating hundreds of times each second. Gravity transforms into motion. Motion transforms into heat. The universe constantly converts one form of energy into another through processes both violent and elegant at the same time. And yet, even in these dramatic systems, the neutron star itself remains astonishingly compact. If Earth were somehow compressed to neutron star density, our entire planet would shrink to roughly the size of a small mountain. Every ocean, continent, atmosphere, forest, and city would collapse inward until all familiar structure disappeared completely. The atoms composing mountains and living creatures alike would be crushed into nuclear matter. humanity's entire world would become a tiny dense sphere. That comparison helps reveal just how extreme neutron stars truly are. They are not simply dense stars. They are matter transformed into an almost entirely different state of existence. Perhaps this is why neutron stars continue appearing so often in science fiction and philosophical thought. They force us to imagine conditions utterly disconnected from ordinary experience. Near their surfaces, gravity distorts time noticeably. A clock placed close to a neutron star would tick more slowly compared to one far away in space. If someone could somehow survive observing from nearby, they would experience time itself differently from distant observers. Einstein's relativity becomes physically real there, not just abstract mathematics in textbooks. And this bending of time carries a strangely emotional feeling when considered quietly enough. The deeper gravity becomes, the slower time flows. Massive objects literally reshape the passage of moments around them. The universe is not built upon one universal clock ticking evenly everywhere. Time stretches and bends depending on mass, motion, and gravity. Neutron stars remind us that even time is not as stable as human intuition assumes. There is another reason astronomers treasure pulsars so deeply. Their extraordinary precision allows scientists to search for tiny disturbances passing through space itself. By monitoring networks of pulsars across the galaxy, researchers hope to detect enormous gravitational waves generated by supermassive black holes orbiting each other in distant galaxies. In this sense, neutron stars become tools for listening to movements happening across the universe on scales almost impossible to comprehend. Dead stars helping humanity hear the slow collisions of galaxies. The cosmos is filled with connections like this. Objects formed through collapse become instruments for discovery. Catastrophe becomes information. Ancient explosions become the atoms of future civilizations capable of studying the explosions that created them. The universe seems almost recursive in its structure, constantly folding endings into beginnings and beginnings into endings again. And perhaps neutron stars embody that cycle more clearly than almost anything else. They are born from destruction yet survive for immense spans of time afterward. They scatter elements necessary for life while also revealing the deepest limits of matter and gravity. They are both tombs and creators, endings and foundations. Tiny remnants carrying the memory of stars that no longer exist. Some neutron stars may eventually cool until they become nearly impossible to detect at all. Over unimaginable stretches of time, they will fade into cold darkness while still retaining their crushing density and warped gravity. Long after their light disappears, their mass will remain, silent and invisible, drifting through the expanding universe. Imagine such an object crossing the darkness trillions of years from now. No nearby stars illuminating it. No planets orbiting it. No life observing it. Only a cold neutron star continuing its endless journey through a universe growing older and dimmer around it. There is something hauntingly peaceful in that image. a final remnant of ancient stellar fire still existing after almost everything familiar has faded away. And yet, even then, the neutron star would continue carrying within itself the same invisible quantum resistance that saved it from collapse billions or trillions of years earlier. Deep inside, neutrons would still refuse identical existence. Gravity would still press inward. Quantum mechanics would still push back. The balance would continue silently in darkness long after the bright age of stars had ended. Perhaps that is the deepest lesson neutron stars offer us. The universe is not built from permanence, but from temporary balances sustained against collapse for as long as possible. Stars balance fusion against gravity. Galaxies balance motion against attraction. Even atoms balance forces invisibly within themselves. Reality survives through tension, and neutron stars are among the purest expressions of that truth ever discovered. Tiny collapsed stars holding themselves together at the edge of annihilation through laws so strange that they sound almost impossible. And yet tonight, scattered invisibly across the Milky Way, they continue enduring exactly as the universe demands. If you step back far enough, neutron stars begin to feel almost like the universe thinking out loud about its own limits. They exist precisely where the familiar order of reality starts breaking apart, where gravity becomes strong enough to crush atoms, where quantum mechanics becomes powerful enough to resist collapsing suns, and where matter itself may transform into forms humanity still does not fully understand. They are objects balanced at the edge of multiple impossible boundaries all at once. And perhaps that is why they continue haunting both scientists and dreamers alike. Because neutron stars are not merely extreme. They are transitional. They stand between worlds, between ordinary matter and black holes, between classical physics and quantum uncertainty, between visible structure and total collapse. They are cosmic thresholds made real. Even their surfaces reflect this strange in-between nature. A neutron star's crust is thought to be unimaginably rigid, perhaps billions of times stronger than steel, and yet beneath that rigid shell lies matter behaving like superfluid quantum oceans. One layer resembles a gigantic crystalline structure while deeper regions flow almost without friction. Solidity and fluidity coexist together under crushing gravity. The star becomes a place where ordinary categories stop working properly. Human language struggles in environments like that because our words evolved for forests, rivers, storms, sunlight, and stone. We did not evolve to describe stars compressed into nuclear matter. We did not evolve to intuitively understand space-time curvature or quantum degeneracy pressure. And yet somehow the human mind still reaches outward trying to imagine these things anyway. Perhaps that effort itself is beautiful. A species born on one small planet beneath a modest yellow star slowly uncovering truths about collapsed stellar remnants thousands of light-years away. Through mathematics, telescopes, radio antennas, gravitational wave detectors, and quiet persistence, humanity has learned to perceive objects no human eye could ever naturally see. We discovered neutron stars not because they are easy to understand, but because curiosity kept pulling us deeper into the cosmos. And the deeper we looked, the stranger reality became. For example, consider how quickly a neutron star can spin. Some rotate hundreds of times every second while maintaining astonishing stability. Imagine standing somehow above such a star while its surface races beneath you at enormous fractions of light speed. Entire mountains on the crust would complete revolutions faster than helicopter blades. Matter itself would be dragged around the star with extraordinary velocity while gravity simultaneously pinned everything downward with crushing force. And despite these impossible conditions, neutron stars remain astonishingly precise. Pulsars act like cosmic metronomes ticking across millions of years. Some are so regular that astronomers use them to test whether the fundamental constants of nature have changed over time. Think about that quietly for a moment. Dead stars spinning in darkness have become instruments for measuring whether the laws of reality themselves remain stable across the universe. The cosmos is full of strange poetry like this. Objects born through collapse become guides for understanding existence. The remnants of stellar death help humanity study time, gravity, matter, and space-time itself. Even destruction leaves knowledge behind. And still neutron stars continue surprising researchers with new mysteries. Recently, astronomers have begun detecting objects whose masses sit awkwardly between known neutron stars and black holes. These strange bodies occupy what scientists sometimes call the mass gap, a region where few objects were expected to exist. Are they unusually heavy neutron stars? Tiny black holes? Something else entirely? Once again, the universe refuses simple answers. This uncertainty matters because neutron stars already push known physics nearly to its breaking point. If some can survive at larger masses than expected, then the internal structure of dense matter may behave differently from current theories. Perhaps quark matter stiffens under pressure. Perhaps unknown interactions emerge inside collapsed stellar cores. Every surprising neutron star forces physicists to reconsider assumptions about matter itself. In this way, neutron stars are still active frontiers of discovery, not solved chapters of science. And beyond all the technical details, there remains something emotionally profound about them. They remind us that reality is layered more deeply than appearances suggest. The calm sky above Earth hides unimaginable violence and unimaginable beauty simultaneously. Invisible collapsed stars drift silently through darkness, carrying enough density to warp time itself, while life on small planets continues beneath quiet atmospheres, almost unaware of the larger cosmic drama unfolding overhead. There is humility in realizing that the universe is vastly older, stranger, and more intricate than human beings once believed. And yet, despite our smallness, we are capable of understanding pieces of it. Tiny conscious creatures composed of star-forged atoms have learned enough physics to describe how collapsed suns resist gravity through quantum mechanics. The same universe that creates neutron stars also creates minds capable of wondering about them. Perhaps that connection matters, because in the end, neutron stars are not only stories about collapse. They are stories about survival at impossible limits. They are reminders that structure can persist even under enormous pressure. Gravity pushes inward relentlessly, yet something deep inside matter pushes back. Tiny quantum laws hidden beneath everyday reality become strong enough to support entire stellar remnants against destruction. Somewhere tonight, one of those stars is rotating beneath cold interstellar darkness. Maybe it pulses rhythmically toward distant planets. Maybe it drifts alone between the spiral arms of the galaxy. Maybe it waits silently beside another neutron star, destined to collide billions of years from now in a burst of gravitational waves and cosmic fire. But for now, it remains. A dead star refusing collapse. A city-sized sphere heavier than the sun. An object where quantum mechanics holds gravity at bay through laws almost invisible to human senses. And as it turns quietly through the Milky Way, it carries within itself one of the deepest truths modern science has uncovered. That the universe is held together not only by force and destruction, but also by delicate, invisible balances resisting the darkness for as long as they possibly can. And maybe, after traveling this far into the strange interior of neutron stars, the most important realization is not simply that these objects exist, but that they reveal how fragile and miraculous ordinary reality actually is. We spend our lives surrounded by matter that feels stable and familiar. Tables remain solid beneath our hands. Mountains hold their shape for millions of years. Planets orbit stars with reassuring rhythm. The world appears dependable, predictable, calm. But neutron stars remind us that beneath that calmness lies an invisible tension maintained by physical laws operating constantly in silence. If the balance inside atoms were slightly different, matter itself would collapse. If the strong nuclear force were weaker, atomic nuclei would fly apart. If quantum mechanics did not forbid identical fermions from sharing the same state, the structure of ordinary matter would disappear completely. There would be no chemistry, no planets, no oceans, no living cells, no people staring upward into the night sky wondering about stars. Reality as we know it depends delicately upon invisible principles hidden far beneath human senses. Neutron stars make those hidden principles impossible to ignore. Inside them, the quiet rules shaping everyday matter become colossal enough to support stellar remnants heavier than suns. Quantum mechanics, normally confined to tiny scales invisible to human eyes, suddenly controls objects spanning entire cities. The smallest laws of existence become powerful enough to resist one of the strongest forces in the universe. And yet, even neutron stars cannot survive forever under every condition. That truth lingers quietly beneath everything we have explored tonight. There is always a deeper gravity waiting beyond the limit. Add enough mass, compress matter far enough, and eventually collapse resumes. The neutron star crosses the final boundary and becomes a black hole, an object so extreme that even space-time closes inward around it completely. This creates a profound continuity across the cosmos. Stars live through balance. White dwarfs survive through electron degeneracy pressure. Neutron stars survive through neutron degeneracy pressure and nuclear forces. Black holes emerge when every known resistance finally fails. Each stage represents matter responding differently to gravity as compression intensifies. The universe moves gradually from familiar structures toward deeper and stranger forms. And perhaps that gradual progression mirrors something larger about human understanding too. The deeper science explores reality, the stranger it becomes. At first, the cosmos appears simple. Stars shine, planets orbit, space seems mostly empty. But deeper investigation reveals curved space-time, quantum uncertainty, invisible dark matter, gravitational waves, and collapsed stars where time itself slows under immense gravity. Reality becomes more mysterious, not less. Neutron stars sit directly within that mystery. They are among the clearest reminders that the universe does not organize itself around human intuition. Nature follows its own rules regardless of whether those rules feel comfortable or strange to us. A star can collapse until atoms vanish and still survive because quantum mechanics demands it. Space can bend. Time can stretch. Matter can become denser than atomic nuclei. The universe allows all these things calmly and naturally. There is something strangely peaceful about accepting that vastness. Human beings are small compared to neutron stars, galaxies, and cosmic time. But we are also participants within the same universe that creates them. The iron in human blood was forged in ancient stars. The calcium in bones emerged from stellar fusion long before Earth formed. The atoms composing our bodies have traveled through cosmic cycles of collapse and rebirth stretching across billions of years. In a very literal sense, the universe became conscious enough to study itself through living minds. And those minds looked outward into darkness and discovered neutron stars. Perhaps that is one of the most beautiful parts of science. Not domination over nature, but relationship with it. Curiosity connecting tiny human lives to gigantic cosmic processes. The realization that even the strangest objects in existence still follow patterns understandable through patience, mathematics, and imagination. Somewhere tonight, a neutron star may be spinning hundreds of times each second while emitting radio pulses across the galaxy. Somewhere else, two neutron stars may be orbiting closer and closer together, destined to collide millions of years from now in a burst of gravitational waves and heavy elements. Somewhere deep inside another neutron star, matter may already exist in forms humanity has not yet fully imagined. And all of it unfolds silently above sleeping worlds. There is a certain comfort in that silence. The universe does not rush. Neutron stars can survive for billions or even trillions of years. They drift patiently through darkness while galaxies slowly evolve around them. Long after human civilizations disappear, many neutron stars may still remain, carrying within themselves the memory of ancient stellar explosions from a younger universe. Imagine one of those distant futures for a final moment. The cosmos colder and dimmer, fewer bright stars burning in galaxies, vast stretches of darkness expanding quietly between islands of fading light. And drifting through that ancient universe, neutron stars continue their endless journeys almost unchanged. Tiny dense remnants balanced delicately against gravity by invisible quantum laws. Silent survivors from an earlier cosmic age. There is something deeply moving about that image. Not because neutron stars are gentle objects. They are among the most extreme things known to science. But because even in their extremity, they represent endurance, resistance, structure surviving at the very edge of collapse. Perhaps that is why they feel strangely beautiful despite their violence. A neutron star is what remains when almost everything else has been stripped away. No ordinary atoms, no fusion fire, no vast glowing surface, only compressed matter, warped space-time, and invisible quantum pressure refusing to surrender completely. And somewhere deep inside that resistance lies one final quiet truth about the universe itself. Reality is not built only from collapse and destruction. Hidden beneath the stars, beneath atoms, beneath gravity, there are laws that preserve structure against impossible odds for as long as existence allows. Tonight, somewhere beyond the constellations above Earth, one of those dead stars is still holding the darkness back. And perhaps now, after drifting through collapsing stars, quantum mechanics, warped space-time, and the silent endurance of neutron stars, we can return to the original mystery that began this journey. Why do neutron stars not collapse? At first, the question sounds simple, almost mechanical, like asking why a bridge remains standing or why a planet stays in orbit. But hidden beneath the question is something much deeper. Because neutron stars should collapse according to almost everything human intuition expects about gravity. They contain more mass than the sun compressed into objects smaller than cities. Their gravity is so overwhelming that ordinary matter would not merely break there. It would cease to exist in recognizable form entirely. And yet somehow the collapse stops. The answer in the end is not fire, not motion, not ordinary pressure. It is law, invisible quantum law. The neutrons inside the star resist being compressed into identical states because reality itself forbids it. The particles are fermions, and fermions refuse complete sameness. From that refusal emerges degeneracy pressure, a strange quantum resistance powerful enough to support entire collapsed stars against gravity. The same hidden principles shaping atoms and chemistry become, under extreme conditions, the final defense preventing total collapse into black holes. There is something profoundly beautiful about that idea. The universe preserves structure not through brute force alone, but through rules woven deeply into the fabric of existence. Tiny quantum laws hidden beneath ordinary life become guardians against cosmic annihilation. And yet neutron stars also remind us that every balance has limits. If enough mass accumulates, gravity eventually wins anyway. The star crosses beyond the final threshold. Space-time curves inward irreversibly. A black hole forms. Even quantum resistance cannot survive forever against infinite compression. So neutron stars exist within a temporary truce between opposing truths. Gravity pulls inward endlessly while quantum mechanics pushes outward. Neither fully conquers the other. The result is one of the strangest objects in existence. A dead star surviving through invisible microscopic laws operating on a cosmic scale. Perhaps that balance mirrors the universe more broadly than we realize. Everywhere we look, reality seems suspended between competing forces. Expansion and gravity, order and entropy, light and darkness, creation and collapse. Galaxies form because gravity gathers matter together, yet stars shine because fusion pushes outward against collapse. Even life itself exists through delicate balances maintained briefly against decay. The cosmos is not static. It survives through tension, and neutron stars may be one of the purest expressions of that truth ever discovered. Somewhere tonight, while Earth turns quietly beneath clouds and oceans, neutron stars continue drifting through the Milky Way. Some pulse rhythmically like distant heartbeats hidden among the stars. Some travel invisibly through interstellar darkness after being thrown outward by ancient supernovas. Some orbit companions closely, slowly gathering matter while approaching the final boundary between neutron star and black hole. Others may already contain exotic states of matter humanity has not yet fully understood. All of them carry within their tiny surfaces one of the deepest mysteries modern science has uncovered: that the smallest laws in nature can shape the destiny of stars. It is easy sometimes to imagine the universe as cold or indifferent, and in many ways it is. Gravity crushes stars without mercy. Supernovas erase solar systems. Black holes swallow light itself. But neutron stars reveal another side of reality too. Beneath all the violence lies structure, pattern, resistance, invisible laws preserving order against collapse for as long as physically possible. And perhaps that is why these stars continue feeling strangely emotional despite all the mathematics surrounding them. They are not simply astronomical objects. They are reminders that existence itself is fragile and miraculous at the same time. The atoms in your body remain stable because of the same quantum principles holding neutron stars together. The matter around you feels solid because fermions resist occupying identical states. The universe that allows oceans, forests, breathing creatures, and conscious minds is built upon the same invisible architecture, preventing collapsed stars from disappearing completely into black holes. In a sense, neutron stars are not separate from us at all. They are extreme reflections of the same physics shaping ordinary reality every moment. And perhaps there is comfort in that connection. Human beings often feel small beneath the cosmos, and in many ways we are. But we are also woven from the same universe we study. The calcium in bones, the iron in blood, the oxygen carried through lungs, all were forged in ancient stars long before Earth existed. Some heavy elements within our world may even trace their origins to neutron star collisions billions of years ago. We are part of the same story. Tonight, somewhere far beyond the visible constellations, a neutron star is turning silently through darkness. Gravity presses inward with unimaginable force. Quantum mechanics pushes back invisibly from within. The balance holds for another second, then another, and another. A tiny dead star continues surviving at the edge of annihilation. Perhaps long after humanity disappears, many neutron stars will still remain drifting through an aging universe. Silent remnants from an earlier era of stars. Dense embers carrying ancient memories of supernovas and collapse while galaxies slowly fade around them. They may endure across spans of time so vast that human history becomes smaller than a heartbeat beside them. And still the same quiet resistance will continue deep inside their cores. Neutrons refusing sameness. Quantum laws holding gravity back. Reality preserving structure against darkness for as long as it can. Because in the end, that may be the deepest truth neutron stars reveal to us. The universe is not built only from collapse. Hidden even at the edge of destruction are laws that continue whispering one final answer into the dark. Not yet.